the idea here is putting molecules in the middle, but by evaporation. While what I am proposing is to use molecules that you put in the middle, not only by evaporation, but also by solution techniques. What I have shown you before is by solution. Then that's why it's important that chemists, because we have it's more rich, we can put molecules in which we can play with solutions, and are still working as spin valves. This is completely new for the people working in spintronics. They don't like to work in solution, and I have shown that in solution it's also possible to produce spin valves.
Thank you, sir. As you know that we are running time short, because already we have to start new session at 7:30, that is cultural programs. Already we are late near about 1 hour, by 1 hour. So I request all the authors to please complete their presentation within 5 minutes. So each and every author will get 5 minutes within. So try to understand the problem also. So I request today's first author, this session's first author, Dr. Alla Jak, Head of Materials Group. Okay. Helen Institute of Technology, Israel.
Meantime, I will use this time to thank the organizer of the meeting. We really enjoy the wonderful organization and incredible hospitality. We're very, very thankful and enjoy our being here in India. And my special thanks to Professor Yakmi, who not only help us to come here and to be in India, also help us to recognize the history and culture of this country, being with us a few days. So thank you very much. And I think I will start. Yeah, it's okay. I will take you back to the synthesis of inorganic nanoparticles. You had today in the morning the first plenary lecture of Professor Reshev Tene, and as a former student of him, I continue in this field, and I will give you a bit information of how we synthesize these materials, one of them, and a few applications. I hope I will be possible to do this. Okay, so inorganic nanoparticles, fullerenes and nanotubes were discovered in 1992 in the laboratory of Professor Tene, as you know, and from this time already 20 years passed over, and a number of groups were tried to synthesize inorganic nanotubes. I will talk today only on inorganic nanotubes, not fullerenes. And so, for example, you can see here two pictures, one of them, and all these, before I continue, I would like to say that there is different ways to do these materials, and these attempts show different chemical roads. So one of them, this is an attempt of, the work was done in the laboratory of Professor Sena Rao. He succeeded to synthesize inorganic nanotubes of tungsten disulfide, also of molybdenum disulfide, by simple decomposition of ammonia thiotungstate at high temperature, obtaining these nice and very thin nanotubes. But this process was not of pure and did not continue to scale into big production. On the left, we can see the experiment which was done in the laboratory of Professor Tene, which result in pure phase of nanoparticles, inorganic nanotubes, but this process was not scalable. It was not possible to prepare enough amounts to study it further on. This process was started from tungsten and through suboxide and different setup, and afterwards these prepared nano whiskers were sulfidized at high temperature in the presence of hydrogen sulfide and hydrogen, and beautiful nanotubes were obtained. So I will show you now the production. So actually this work inspired me to try to synthesize these nanotubes, which I will show you in a few minutes in big amounts. So actually today we can produce up to 100 gram or half kilogram or kilogram per week of inorganic nanotubes, pure phase. So this process based on a precursor material which is tungsten suboxide. And you can see here the picture of first 1 gram and then a bottle of, you already see this picture. So I will go to a few details of synthesis. So the synthesis is not simple. It's high temperature, but working hard, we succeeded to get good results. So we actually start from small nanoparticles of tungsten suboxide. You hear in parallel in scheme and also real pictures from SEM and TEM. So this is the starting materials, mixture of suboxides, nanoparticles, and this is how it looks like on SEM picture. Then you put this powder into the reactor. In the reactor you have from 750 to 900 degrees the presence of hydrogen and hydrogen sulfide, and in a few minutes you see the growth of long nanoviscers of tungsten suboxide, already a little bit reduced phase compared to initial one, and after 5 minutes the sulfidization sulfidization started, and we can see a few layers on the external on the surface of the nanotubes. This is another picture. So in order to get these pictures, I stopped the reaction after 2 minutes, 5, 10, and so on, and studied this material in a microscope. And actually, after 6 hours of the reaction, depending on the size, we can convert all oxide whiskers to this sulfide. It is a very interesting reaction, but I cannot explain to you. Everything is happening in the same reactor done from quartz. It is special glass which is stable at the high temperature. And also, we can say that it is one spot reaction where two processes take place. Growth of whisker. I have no pointer. It's crazy. Long whiskers are grown, and also afterwards sulfidization happened. So XRD confirmed this, but I will skip. I want to show you first of all these beautiful pictures of nanotubes we had obtained. This is the first was SEM. This is the TEM picture. So actually, these particles scale their size from few microns to 50 microns, and average from 10 to 20 micron, and in the size, in the diameter, they average 100 nanometer. They're bigger than carbon nanotubes. They have another properties. So. One of the application of this material, which I could touch now for these few minutes, it is preparation of nanofibers from polymer, and this is the method which was applied to prepare these nanofibers, so-called electrospinning. So you have this solution of polymer, you put into the solution dispersed nanoparticles. The solution is of a very small viscosity, thus it could be could go through the nozzle of spring, and under the very big electrical field of 16 kilovolt, or depends on the solvent, up to 30 kilovolt, you pull this drop and create very long and thin nanofibers of polymer. So the solvent evaporates and you have solid fibers, and nanotubes are inside and aligned as due to this setup. So you can see this, the diameters of fibers which could be obtained 0.2, 1.5 micron, and different collectors where you could gather this material. So actually, one of the examples you can see here, this is a picture of, this is the same image of fibers done from PVDF polymer. You can see here the TEM picture where you see one fiber with nanotube inside. So this technique align these nanotubes, and when you take these fibers and collect them in correct way, you can also align these fibers, and by this way align the nanotubes. Or you can prepare a woven collection of these fibers, and then you can do everything. For example, when you not everything, but many things. For example, when you work with PVDF, which is piezoelectric polymer, and you put inside semiconductor nanotubes, which could be also doped, and you can control their conductivity, and you can control also their magnetic properties in special doping. So you can prepare different devices, which is now in the process. We are working on this, and another possibility, we prepare PMMA fibers. This work was already published and was done together with group of Professor Eyal Zussman from Technion. You already hear today this name, the institution in Israel, and we prepare these beautiful fibers. It looks like a small mesh, very soft and thin, like you see here, and SEM microscope on the high resolution. You can see how it looks like. And also one small term, you can see nanotubes, small lines, which is inside the nanotube. So beautiful results were obtained, which show that when you embedded these fibers with nanotubes, you influence very much mechanical properties of this polymer composite. Actually, you can see on this graph stress versus strain. Stress versus strain, and you can see, so by calculating the angle of these curves in the beginning, where the line is strain, you can calculate the Young modulus, and you can see that comparing with neat material which contain nanotubes, improve with Young modulus P10 or P20 times. So, which is a very important and interesting result. And you also could see in this table that different parameters improved: tensile strength, ultimate strain not, but Young modulus and toughness indeed. And this is the most important parameter, which shows us the energy which you should apply to broke this material. And you also could see here the importance of the concentration when we prepare composites